Thank you for joining us today. We have a very interesting session today about best practices for high availability in OpenShift. My name is Sauvegarde Kimchi. I am a senior cloud architect in the professional services at Red Hat. So what we are going to discuss today, the challenges for high availability in disaster recovery and best practices from the field, and how we can combine this all together. Also with me, we have a special guest.
So my name is Christina Wong. I'm a former Red Hatter, and I currently work at NewADB in charge of product marketing and partnerships. And while I was at Red Hat, I was in charge of JBoss EAP and talked a lot about microservices and DevOps. And at NewADB, kind of brought the container conversation into the picture. And I insisted that my co-presenters add something fun about themselves to help wake everybody up, because you guys are like skipping first part of lunch to be here. I appreciate that. So in my spare time, I race cars and also work on cars. That's a lot of what I do. On the weekends, first car race is coming up this weekend in Philly, the Philly area. So Arif, would you like to introduce yourself?
My name is Arif Qassam. I'm VP of Product at NewADB, so I'm in charge of sort of product roadmap strategy. I joined NewADB a couple years ago from Teradata, so I've been in the data space for a long time now. I think the partnership that we have with Red Hat is a very good partnership, and I think what you'll see today in terms of high availability and disaster recovery for the entire application stack on OpenShift, I think the partnership between Red Hat and NewADB provide a very good solution for you guys as you develop your applications. And the funny thing that I'm a Canadian, so that's the only thing I could come up with.
So I'm going to kind of set the stage for everybody and then let these guys take over and talk about the best practices part of it. Kind of when we think about high availability and disaster recovery today and what CIOs really need for their organizations, it's changed from what they needed in the past. And so it's really important today that there are no outages, because when there's outages, it's bad PR, it's really expensive, you lose business, you lose customers. You're required to always be on, right? Users sign into the application, they expect it to be working. You need to provide service 24/7 by 365, right? And because of these requirements, the implementation for applications has changed. And the way that people think about building applications and high availability into applications has changed. And so, processes like DevOps and CI/CD become really important. Doing things like being able to do rolling upgrades, whether we talk about local or across multiple environments, becomes really important. Building redundancy into the system, that's really important, right? Because you can't have something go down and then the entire thing go down and everything gets broken. High availability architectures, microservices, using containers, that's something that we talk about a lot these days, at Red Hat Summit and across the board, in the software industry. Operational processes like failover, these are all ways of implementing high availability into systems that help meet the expectations of customers today when they're using the software, with the end goal being continuous service delivery. And yesterday's technologies, they're no longer acceptable to use to meet today's requirements, right? From the app dev and operations perspective, people are continuously talking about breaking down their monolithic application into microservices, into smaller pieces, right? And using containers to do that. You can't have tightly coupled integration anymore, because you make one change and it requires downtime or update in the entire system, or if that one thing breaks, then everything comes with it and breaks down. That's not acceptable for high availability. When you have tightly coupled systems and tightly coupled development groups and monolithic architectures, it's just really slow to make changes. You can't be agile. You can't move at the pace that you need to move to deliver new features. And with manual processes, once you put a human in the mix into things, it slows everything down. From the data infrastructure side, this is the same type of conversation. The data center, has become kind of an anchor, right, to a lot of organizations, and people really struggle to figure out how to build, agile microservices, types of applications, but then answer the question about what to do with the data in the data center. when the resources that a data center takes up, that the infrastructure managing that takes up, isn't an agile type of thing. It's a lot of resources. It's very complex. It's complicated. It's hard to manage. Scale up versus scale out. We all talk about scale out these days because it's so much easier to just add on another server versus migrate everything over to like a bigger server and incur the downtime and costs that associated with that. So the thing is that when you look at traditional solutions, when you add high availability into those solutions, it's very complex. It makes the system more complicated. And that's really no longer acceptable in this day and age when we're trying to provide continuous service delivery and to provide agility into the system. So I'm going to talk a little bit about disaster recovery and traditional database approaches with disaster recovery. This is an example from Oracle, right? And this is how Oracle solves the high availability disaster recovery problem, right? You need to add on so many different technologies, RAC, Golden Gate, Active Data Guard to get high availability, to accomplish clustering, to get active-active. This stuff is expensive. It's really hard to set up. It's hard to manage. It's hard to maintain. I mean, can you imagine trying to do this in a container environment? It's impossible. You need special networking. You need special hardware. You can't do it in a container environment, right? And so this is not a great way of going about building today's applications. It's really expensive and really difficult. And when we talk about disaster recovery, we can go through. I'm just going to quickly go through the spectrum of disaster recovery, right? Cold standby, not acceptable for high availability continuous service delivery these days. Cold standby, you have another data center offline. If your active data center goes down, you need time. You have downtime. You have data loss until you can bring up the cold standby data center. It's probably not going to have the latest data that the active data center had when it went offline. Warm standby is a little bit better, but you still have offline, you still have gaps in data from the situation. Data loss is highly likely depending on the last time the replication occurred. For hot standby, you run into the utilization conversation. Okay, you have this entire data center which is active and running applications and taking up your people and your resources, right? And so if your current data center, the active data center fails, well, that's great. You don't experience a loss of service, but at the same time, you have an entire expensive data center sitting there that's not being used at all. So maybe you can increase the utilization by adding read capabilities to that the standby data center, which is great for additional read throughput, but you're still not fully utilizing that massive resource. So let's say that you want to fully utilize both data centers. Maybe you could implement an active-active approach. But as we saw from the previous slide with the Oracle example, the traditional ways of doing that is really expensive and really complicated and really difficult. It's a huge headache. And so you are only going to do this if you feel like that you absolutely need it and you have a huge business case to justify all of that, right? But today, even the most simple applications need to be always on and always available. So are you going to spend that much money and that time and effort, even for simple applications? You're probably not, right? It's a difficult trade-off that you're forced to make if you want to go with traditional approaches. So I hope that sets the stage for our conversation today. I'm going to let these guys take over, and they're going to talk about best practices from the field to achieve high availability and modern disaster recovery without having to make all these compromises.
Okay, so when we are designing HA architecture for OpenShift, we have three options to have it. Design the HA on a single site, okay? Second, using a DR approach when we have active and standby. And we can also have a multi-site application where we have active-active or three separate data centers. Now, I would like to start if you design a HA architecture for OpenShift, you need to consider all the layers that are the building block of the cluster. So I will explain how to achieve on each layer of OpenShift, how to achieve the HA capabilities. And we can see how all the layers are working together. So the first layer that I'm going to discuss is the master. Okay, they're responsible for the OpenShift API and also the OpenShift console. In terms of best practices, to have three masters, okay, and a load balancer in front of them. This way we can achieve HA. The second tier is the etcd, which have a built-in clustering mechanism, okay, when I provision the cluster with 3 or more etcd nodes. The etc layer are responsible for the persistent layer, for example, storing the secrets or any data that I need to have a persistency for it, okay, for the cluster data, okay. So I can use the built-in mechanism. The other layer that I need to consider is the infranodes layer, okay. In the infranode layer, I have the routing layers, the routing pods, sorry, that actually route all the traffic from the external world into the OpenShift cluster. In addition to that, if I provision the ocular in order to see metrics, performance metrics, CPU utilization, memory utilization, also I can deploy it in a cluster way. Another layer that I can deploy is the EFK, when I can have a centralized logging in order to analyze all the pod logging. So here I can also define the EFK in a cluster mode. Okay, so I have high availability. So for example, if one of the infranodes is going down, still I can access to my Kibana UI. I can see the metric from all my pods. So for this layer, the same as the master, I can define a load balancer that actually can move the traffic from the load balancer into the infranodes. This way I can get HA. Now, the fourth layer is the app node where my actual pods are running, my application pod is running. So in terms of best practice, more than one app node, of course. So in case of unscheduled or scheduled downtime, the pods can be revoked to a different node, or OpenShift can move the pods automatically. Now, for the storage layer, in order to get HA capabilities, OpenShift supports a lot of storage plugins such as Ceph, Gluster, VMDK, etc. And if I want to design HA for my clustering layer, I can use it as a Gluster. Okay, I can provision it over a virtualized environment, for example. So I can have two Gluster cluster. The first one will be responsible for the, let's say, the infranodes, okay? And this Gluster cluster will be responsible for the registry HA, okay? So I can define multiple pods of the OpenShift registry, and the Gluster can provide me the storage backend for this. Okay, for other storage needs, I can use the second Gluster storage. Okay, the reason that I'm separating this is to avoid that, let's say, disk I/O utilization that can affect the registry, and if the registry is not functioning as well, it can affect the entire cluster. So here we saw how we can, in terms of infrastructure, how to design the cluster for HA capabilities. Okay. Now, infrastructure is not enough. I need to consider what I can do in my application layer. Okay, so how I design my application, or how I design other OpenShift feature in order to have HA. So the first thing is, for every service that I add, to have at least 2 pods. So in case of one of them is going down, the application is still able to provide traffic. I can do this in more automatic fashion by providing pod autoscaling. What is pod autoscaling? Pod autoscaling is a special pod that actually, using the ocular metrics, based on those metrics, for example, CPU utilization, it can actually initiate more pods if, for example, my CPU utilization of my pods is exceeding 18%. So it will create automatically mode pods for my application. This way I actually providing HA using the pod autoscaling. Another approach is to actually define my application using a stateful set. So stateful set allow me to provide an identity for each pod, and each pod, and also to the storage layer that is actually using. And for example, if I want to define a Kafka cluster, so I can define a stateful set where all the storage need and all the, let's say, the interconnection between the pods, which pods can start, what is the ordering of starting the cluster. Another approach is to use a built-in the liveness and readiness probe. So those probes are implemented inside OpenShift, and actually those probes are monitoring my pod. Okay, for example, listening for port 8080. Okay, and in case of that I'm not receiving 200 OK response, it will restart this pod or revoke it and move it to another OpenShift compute node. So I can see a built-in HA mechanism inside OpenShift for the pods that I'm running. Another idea is to achieve HA is to tune my pods. Okay, why I need to tune my pods? For example, one of the customers that I'm working with need to address network spike very quickly. Okay, it's a telco provider, and it need to address to respond very fast. So in order to achieve this kind of responsibles from his application, you need to initiate as many as pod per second. So we test it and benchmark it. We're able to achieve, let's say, 20 pods per second, okay, using their pods. And we managed to do this by tune the pod, okay. Also, the OpenShift provided images are auto-tuned themselves, okay, based on the allocated memory. But if you have, let's say, a custom image that you built for your application, so using the quota and limit capability of OpenShift, you can also tune this. Another, let's say, ability is using node labels and node selector. So using node labels and node selector, I can actually tag my OpenShift node based on, let's say, the rack that those nodes are allocating at. Also based on the data center, okay, or the zone if I'm on a cloud environment. This way, when I'm deploying a new application, I can define on which compute node my application is going to run. So for example, I want to make sure that my application is running on 2 separate racks in order to avoid the situation when one of my racks is going down with all the server, my application also goes down. And another example is using on a cloud environment. I can actually tag my nodes based on the availability zone that they are located. And this way, even if one of the availability zone goes down, still my application can receive traffic. Now, when I'm designing disaster recovery for OpenShift, now I'm switching to multi-site, the multi-site approach. So I need to think about how I can actually replicate the project or namespaces, the images, okay, and the persistent volume. So for every object in OpenShift is based on YAML or JSON configuration, so I can actually export those objects and import them to a different OpenShift cluster. There is an ongoing project to do this kind of backup. It's in GitHub. Okay, so you can actually take all the objects from one cluster and import them to a second cluster. Another approach is actually how can I leverage my CI/CD pipeline to do the synchronization between the cluster. Anyhow, most of the customers are using the pipeline in order to deploy application, to update the application. So why not leveraging this mechanism in order to deploy it not on a single site, but also on the DR and also the prod or any other data center that I'm deploying the application. So how can I leverage my CI/CD to synchronize all the objects that I need to have synchronized between the different clusters? Now, the most challenging aspect of synchronization between different OpenShift environments is how I synchronize my storage. Okay, so a brief introduction to OpenShift storage. We have the PVs, the persistent volume. Okay, that actually provides us an abstraction layer above the, let's say, the storage subsystem, which can be a Gluster, Ceph, EBS, or other storage backend. And I have the PVC, the volume, persistent volume client that actually the pod claim in order to get the PV, and the PV connect to the storage backend. So now, if I have two clusters, how can I actually synchronize the data between the two clusters? So one approach can be using GER replication, for example, for Gluster. So I can actually replicate the storage across multiple data centers. So here the challenge, I have duplicating my data, and also the performance of the network can affect the replication. And also another approach, which is, I think, better, is that the application tier or the database tier can actually replicate the data for me. Okay? So as a developer, I don't need to build some kind of replication mechanism between the different data centers. So so it's actually taking care for me for this kind of scenario of replicating the storage. Another thing to consider when I have multi-active OpenShift is the network latency, where it's important. If I want to do a stretch cluster, what is a stretch cluster? Stretch cluster is OpenShift cluster that resides on two separate data centers. And the challenge here is that I need to have, let's say, 2 milliseconds between the ETC nodes. So if I don't have this kind of network latency, strange things can happen. So I need to consider that. Another approach to have a stretch cluster is that the etcd and the master on one data center and the compute nodes on a second data center. Here I need to take care the latency between the master and the nodes. It's not restrictive as the etcd, but again, I need to consider this latency. So I need to make sure how I can design this kind of solution.
Thanks, Orgad. So as Orgad talked about the best practices and configurations for high availability and disaster recovery for your OpenShift cluster, one of the things he points out, quite rightfully so, is the storage layer is difficult, right? All your applications require some sort of data typically, and that data needs to be consistent and available across either internally on a single node, a single cluster, or multiple clusters. And to get across multiple clusters, or even within a single cluster, there are either manual steps that you can do at the application layer, there are manual steps or sort of automated steps you can do at the storage layer. But generally speaking, as a developer, we believe that you shouldn't be worried about how to manage replication and consistency of data across a single site or multiple sites. You want your data available, you want your data consistent, you want your data in both sites. Right? And so as a NeoDB, a certified Red Hat partner, right, what we provide is a container-native SQL database that allows the data to be fully replicated on a single cluster and across clusters. So NeoDB, we're a company based in Boston, right? We're started in 2010, so we've been at this for a long time. And the fundamental difference between us and other databases is that we started as a distributed system, a multi-process, multi-node system with database capabilities built on top of it. We're not taking an existing database that was designed 30 years ago, architected 30 years ago as a single system, and adding capabilities to make it replicated or to make it consistent across multiple nodes. Christina showed you that Oracle slide, right? Oracle requires Golden Gate and RAC to get multi-nodes and replication across multiple sites. And that's just two of their many products that they provide, right? So as a distributed database, think of us as sort of a NoSQL architecture, but fully transactional, fully SQL, fully ACID, with indexes, with joins, everything you expect from a traditional OLTP transactional database. But since we started out as a distributed system, replication is inherent to our system. It's automatic. You add nodes, the data is automatically replicated. You take nodes away, it doesn't matter, right? You've got multiple nodes available to service your data application requirements. And that is all seamless within an OpenShift environment. So you can add nodes within a single OpenShift cluster and across OpenShift clusters. And the data is automatically replicated and available in both clusters for you, transactionally and consistent. Because we're SQL and ACID compliant, we routinely migrate customers from Oracle or SQL Server to NeoDB. We also have customers who've migrated from Postgres and MySQL to NeoDB. And the other benefit is that we're fully integrated through a CI/CD pipeline. Right? You can take Jenkins, you can take Ansible, you can deploy NeoDB databases as Docker containers along with your application in the same pipeline. Right? You don't have to have a DBA or another operator to say, okay, now I'm going to go set up a server, give you privileges, give you access, get your data in there, and 2 weeks later, now I can run my application or test my application. Because we're fully distributed and each node, actually, sorry, let me take a step back. The other thing that I need to point out is, unlike traditional databases, we have two layers. We have a full in-memory transaction processing layer. Think of it almost as like a Redis cache, right? Fully in-memory cache. And we have a storage layer, right? Which is your durable points of storage. And that's where your replication would happen across those storage points for durability. Each of these processes can be scaled independently of each other. So depending on your application workload, if your application workload is read-heavy, you can scale out your transaction in-memory processing layer to accommodate your queries. You can co-locate each of these transaction engines with the application container, right? So you can have low latency access to your data right beside your application container. Okay. If you think if you've got a deployment model where you're deploying Redis or some other memcache type of system in your containers, you now have to manage the write to the cache and the write to the database at the same time, right? So the application has to manage the consistency and durability across the caches and the data stores. We're a write-through cache. So once you write to our transaction engine, we automatically make sure it's durable. So you don't have to worry about making sure that data is durable. We handle that for you. So you can scale out the transaction layer, you can scale out the storage layer for additional I/O throughput depending on your workload that you're using. And all this is dynamic. I can add a node, I can remove a node. So long as I have at least one TE and one SM available in my system, my database is up and running. So what we've done with Red Hat, right, is we've provided an OpenShift certified container that runs our database just like any other container that you do for your application servers or for your applications. Right? They can be deployed in a single OpenShift cluster. They can be deployed across multiple OpenShift clusters, and they look like a single logical database across both clusters. Right? And so in this picture, in one cluster, in one OpenShift environment, I've got 3 TEs and two storage managers. And the other side, I've got 1 TE and 1 storage manager. And the dashed open circles represent other nodes or other pods that I can deploy my container to either build out scalability or build out redundancy. So for example, if I, on the right-hand side, deployed another SM in that bottom open circle, as soon as that service is brought up, it automatically joins the NeoDB database and automatically starts replicating the data across to the other side. The DBA, the operator, doesn't have to do a backup and restore somewhere to copy that data. Right? The developer doesn't have to worry about whether that data is over there or not. Right? This is all done transparently, internally, as a service, as our database service to the applications. And the same thing with the TEs. I can add another TE. I can deploy an app in a TE container together in that other site, and I've got now access in terms of an active application deployment model. Right? Trying to do active with stateful applications in containers is very difficult because you have to figure out how you're going to get that data from that one database to the other database in a consistent manner. Again, because we're a distributed database, we take care of that for you. Right? We're transactionally consistent. We're strict consistency. We're not eventually consistent like NoSQL databases. As I mentioned also, we're fully deployable through the CI/CD pipeline that you have today. We support Jenkins, Ansible, all the standard tools from a pipeline perspective. So as your developer, I can stand up a database for my application as I need it, and I can tear it down as I need it. Right? Because everything's built in at the data layer, right, within the database, creating a database is simple. Right? It's a RESTful call to deploy a container through OpenShift, and I can scale that up through my OpenShift controls, just like I scale up any other pod or any microservice container. Right? And again, I can tear it down as I need to. Right? So it enables our developers, our customers, to quickly prototype applications, quickly deploy applications, and quickly scale their applications. We have a large customer in the UK. They're a bank, large bank. They are, as everybody is, as all financial services companies are going through digital transformations, right? And they have deployed NeoDB along with applications in microservice containers so that they can scale up as they need it, right? You could have a deployment of NeoDB fully within the container environment, or you could also, if depending on how you want to architect the system, you could have the storage outside the container, but only the TEs in the container. So there's various different topologies and configurations that you could do depending on how comfortable you are with the environments. So in general, what I want to try to reiterate here, right, is NeoDB provides what I try to use as container native database. It's not taking a Postgres image or an Oracle image or a SQL Server image and putting it in a container, which is effectively just another virtualization model, right? Because we're fully distributed, because we're fully containerized, because we're fully scalable, we fit the same model as application developers expect from a container system, right? It's elastically scalable, fully redundant, fully ACID. So Christina talked about some of the challenges. Orgad talked about some of the best practices on how to deploy and configure OpenShift for HA and DR requirements. And then I tried to walk through some of the capabilities that NeoDB provides to make sure that that at the data layer, developers have a data layer that they can use that is seamless in terms of ensuring availability and replication and disaster recovery for your applications as they need them.